Hello, and welcome to Lecture 4 of Magnetic Fields of Moving Charges in Phys 1204. In the last video lecture, we saw how to use Ampere's law to get magnetic fields, but that only works for high symmetry situations, so now what we need are some more general methods. So we know the B field due to a long straight wire, and we have also seen another high symmetry situation, which is the solenoid. But what we now need to look at is fields due to more general shapes of wires. Well, the approach we're going to take is going to be pretty familiar. We're going to break the wire into little bits. We can think of any wire as a set of short wire segments. Each segment will produce a B field at the location we're interested in, and then the total B field would just be the sum of all those, or more precisely, we have to take the limit as our wire segment lengths go to 0, which turns this into an integral. So since we're going to think of any wire as just a bunch of wire segments, what we need to know is the B field due to a single short wire segment. And I'm going to start with the angle dependence because it shows us how we can isolate a single segment of wire and just look at the B field due to it. And the crucial observation is that if a current is going straight towards or away from the point of interest P, then it produces no field there. So in this arrangement where there are two wires, one going straight towards P and the other going straight away, there's no field there, and you can verify that experimentally. And so now that allows you to isolate a short piece of wire by building your short piece of wire near a point P and having the supply to it be wires coming in and out that go straight at or away from P. The next thing to notice is that the maximum field strength occurs when the wire is going perpendicular to a line joining that piece of wire to the point P where we want to know the B field. And more generally, if there is some angle theta between the wire and the vector pointing at the point P, then we find that the magnitude of the field at P goes as sine theta. We can vary the length of the wire segments that we're looking at, and as long as we use short enough segments that we don't have to worry about the fact that the angle dependence is different at different points along the wire, we find that the magnetic field is proportional to the length of a wire segment that's producing the B field. And finally, we can also vary the distance between the wire segment and the point where we're looking at the field, and we then find that the magnetic field strength goes, like so many other fields we've looked at, as 1 over r squared. So finally, you can put that all together, along with the fact that the magnetic field strength is proportional to the current, to get this proportionality. And so all you now need is a proportionality constant, which in principle you could get experimentally, but in fact this is a defined quantity. And so here is our final relationship between the magnitude of the field at P and the current length of the wire segment, angle, and distance from the wire segment to the point P. All that's left is to come up with how to get the direction. So we want to take this equation and just put a vector symbol over the B. Well, how do we do that? I've been using a convention that the delta L vector points in the direction of the current through that ith wire segment. Using that convention will allow us to come up with a relationship. You can probably guess there's going to be a cross product involved because we're combining two vectors, delta L and RIP, and getting a new vector B, and the new vector B is going to be at right angles to both of them. And we've already seen that there's a sine of an angle, and so these are all clues that there's a cross product. Well, so you just have to work out what that cross product is. You can use the familiar right-hand rule for current, sticking your thumb along the delta L vector here and curling your fingers to verify that the magnetic field at P should be into the page. Then just play around with the three vectors delta L, RIP, and the B field, and you'll conclude that the B field has to point in the direction of delta L cross R. And so we can write our full form for the magnetic field due to a wire segment like this. And this is known as the Biot-Savart law. As always with magnetic fields, the difficulty here is getting all the directions of the vectors right. So practice. Here's a wire, and I've shown which way the current is going in the wire, and a point P, and you should decide which of these trios of vectors for the delta L vector, the RIP vector, and the resulting magnetic field is correct.